Now that our fields are organized by subject, we should have a good understanding of all of the tables that will need to be created in the database to satisfy our mission objectives. Additional tables will be required by the DBMS to operate efficiently, but we'll identify those more thoroughly in the next chapter. The next stage is to begin hooking our tables together in a series of relationships. To do this, we'll evaluate each table against every other table and ask if there is an association between the two entities. In making this determination, it's often helpful to try and verbalize the relationship. For instance, when comparing the employees table to an invoice table, you might say that the employee assists with an invoice, or that an invoice is created by an employee. If you were to compare the invoice with the line items table, you might realize that an invoice is made up of line items, or that line items appear on an invoice. These types of sentences often come directly from the requirements gathering phase and may already be a part of your research documentation. Other linking phrases that you might try include the words has, contains, is made up of, and so on. So continue investigating how the various tables might be related to one another, and as you identify relationships, draw a line between the two tables in the data model. So line items contain products. Invoices are billed to customers. The relationships you'll identify come directly from the mission objectives. In this case, there is no direct relationship between customers and products without going through an invoice. But in another database that has the mission objective to allow customers to write product reviews, there might be a more direct link. Keep in mind that different objectives will produce different data models, even if all of the individual data items being tracked are identical. Once you've exhausted the links between tables for your objectives, it's time to start looking at the type of relationships that we just made. Let's simplify this data model just a bit and look only at the relationship between our customers and the invoices table. We established that the relationship is based on the fact that invoices are billed to customers, or customers get an invoice. There is clearly a link between the two. We can refine our understanding of the relationship by looking at something called cardinality. Essentially, what we want to figure out is how many unique records from each table might be involved in the relationship. To do this, we'll read the relationship from both directions. First, I'll go from left to right and ask the question, each invoice will be related to how many customers? In our case, an invoice will only be associated with a single customer. I can note this on the diagram by placing a number 1 on the relationship line against the customer table. Next, we'll read the diagram from the other direction and ask, each customer will be associated with how many invoices? If our sales team is doing their jobs correctly, we would hope to have lots of repeat business, so the database should be created to allow many invoices for each individual customer. We can note this by placing the letter N on the relationship line against the invoices table to signify some unknown number. What we just created is a one-to-many relationship between invoices and customers. Now, here and there, you might see several different choices in the symbols we place on the lines depending on the background of the data modeler drawing up the design. Sometimes people will place a slash instead of the 1 and a crow's foot design in place of the letter N to denote a one-to-many relationship. Still others will use an infinity symbol to represent the many side. There's lots of variations on the idea, but what we've just now identified is the maximum number of records from each table that will be related. A one-to-many relationship is by far the most common that you'll come across. Other possible outcomes are a one-to-one relationship and a many-to-many. So that's cardinality, the maximum number of records that might be involved in the relationship. We can also take a look at something called optionality, which is the minimum number of records that we can have. To determine this, we'll read again from left to right. An invoice can have a minimum of how many customers? If we have a business rule that says a customer must be attached to every invoice, then the minimum number is 1. And if the minimum is 1 and the maximum is 1, then we've just identified that the customer is a required piece of information that we need to have for every invoice. Let's read it from the other direction. What is the minimum number of invoices that each customer will have? Here, we'll need to look at our business rules to help define exactly what a customer is in our case. We might have a rule that says a customer is someone that is placed in order. If that's the case, then the minimum number of invoices is 1. If our business rule states that a customer is someone that will potentially place an order, then they might have no invoices, in which case the optionality is 0. We can indicate the optionality on our diagram by indicating a range of possible values for each side of the relationship. So we can take this back to our overall data model and fill out the rest of the diagram. A single employee is an optional component of every invoice, but every employee might be associated with 0 or more invoices. An invoice must have at least one line item, and every line item will only appear on a single invoice. A line item will include exactly one product, but each product might appear on multiple invoices. A line item will include exactly one product, but each product might appear on multiple line items, or none at all. So that completes the Two Trees Olive Oil Company model. Now it's time to take a few minutes and complete the relationship designations on your data model.